Okay, everyone. So, how's everybody doing with the semester?
It's good, but last week I cried for some time, and I have problem for the data. I didn't know
Uh,
where go.
so, I definitely get the feeling that we're all sort of rattling towards the finish here. I am. So, at the end of the class, I wanted to talk to everybody here and everybody who wants to chip in online on how to get everybody across the finish line. That is my goal. So, first, so last week we talked about nearest neighbors and the intro to metrics. So that was right at when I did the assignments that sort of hinted at the kind of stuff that I'll be talking about today. Because I call them metrics, but it's accuracy, precision, and recall. Those are the three that we talk about when we're evaluating different machine learning algorithms. So all of these textbooks, which are not required, but now we're at the machine learning part. And so if you have comments on this draft, please let me know, because I can pass them on to Vivienne, and she'll be really thrilled to hear that. So today we'll talk about the performance metrics, so diagnostics, like how well are we doing. And so I think that actually clicks well with the, hey, how well are we doing semester-wise, which I was hoping to do right after that. And so we looked at decision trees, we looked at nearest neighbors, right? So what if we do a classification, we use, it's kind of like deciding somebody's grade by their neighbors, for example. Like you take the three nearest people and go like, how well are they doing? Like, okay, that's their grade. Well, okay, that's your new grade now. That's a way to like just basically decide how people are doing on what table they're sitting. I'm sorry, the example is completely coming from the fact that we're all sitting at round tables. So that's how a k nearest neighbor would work, for example. And so a common weakness is that if you have a machine learning that works well on your training set but extrapolates very poorly, doesn't go on new data sets, doesn't particularly well. Like you've trained it on something and it works great there, so it looks good on paper, but then you try to extrapolate, try to go to new values, and it doesn't work. And so, for example, the nearest neighbor needs to actually scale the data, the whitening of the data, right? So everything normalized so that it trains in every direction equally. Decision tree can only split along features. Basically, you only have yes/no answers. You only can take the road less taken or the most taken, but there's no, in between. There's just split here and no gradients. And so picking the right features, picking the right labels and training set, that's what this all comes down to, right? How do I tell how well I'm doing? And so far, or at least with the last few, we judged it on accuracy, because that feels like, okay, how many did you accurately classify, and how many did you get misclassified, right? That feels like the normal way to do this, except that you can look for something really rare. And then, so habitable planets is our example, but suppose in medical examples, 99 out of 100 people are perfectly healthy, but you really want to get that one person that isn't, right? So it's not an equally weighed accuracy of 99% there is not good enough, because you can say declare everybody healthy, for example, and that's a 99% accurate algorithm, yet that's 100% of what you don't want. And so it's an imbalanced data set. And so that's what we come across in most real world examples, where you go, oh, I'm interested in those, and that's the ones that I really want. And so the accuracy of correct predictions, like how good do I get to the ones that I want? So an imbalance is also the ones that you basically are not interested in 90% of the sample. You're interested in getting that 10% accurately. That's a different question than, did I classify 100% of my sample, or did I get reasonably close to classifying them as 0 and 1s, or the label. And the accuracy paradox is the number of correct predictions. If we get, like we say that all of them are uninhabitable. We saw that, right? We just said, like, well, what happens to like a random classifier that just calls them all uninhabitable? That's 99% accurate. You can go to the press with that. 99% accuracy that all planets are inhabitable. Fantastic headline, completely wrong, right? Because that's not what we're interested. We're interested in that 1% of all the correct hits. So you get what you measure. I love this particular one. It was like, we checked all our nets and concluded there are no fish smaller than this, right? That's what you're doing. You're measuring your tool, not your data. And so the best way to classify this is saying, like, okay, we've got 4 kinds. So we have a positive and a negative, right? So this might feel a little medical at this point, because, you know, I think we all are dealing with positive and negative tests right now. So a positive is the thing that we're after, and a negative is the thing that we're not after. And so we have true positives. This is a positive, and it's accurately measured as such. We have a true negative. This is a negative, and it's accurately measured as such. And then we have a false positive, you know, horrors. So it is reported as positive, but it was a negative. And you have false negatives, the ones that are reported as negative, but were reported as negative, but were a positive. So you can imagine, since my mind is now in the medical, you know, testing thing, and since we are all doing these, you want these to be accurate, and you want these to be as minimized, right? And if everything else being equal, you kind of go like, well, I can live with a couple of false positives, right? That's just a couple of people with their heart racing, and then we'll test them again. They go like, oh, okay, it was fine. But I definitely don't want to live with false negatives, right? So some of them, the desirability of this needs not be equal, right? You can, if you're a medical professional, you can live with a couple of false positives. Fine, we'll rerun the test. Okay, Mr. Johnson is not happy right now because he had to rerun the test and, you know, stressed out for 3 days, but honestly, that's not a huge deal. This is a much worse deal because, you know, now 6 months down the line, somebody comes back like, wait a minute, I actually was sick, I did have something. So, you know, that's massively different consequences. So you have different weights for how desirable each of them are, really, right? If you're looking at this, you kind of go, what are the things that I really want? Well, ideally, I want these to be 0, and I want these to be 100%. Failing that, and we're guaranteed to fail that, then which ones do I care about the most? Do I want the true positives to be, you know, absolutely clear, and there be, you know, very little false positives, and the rest I don't particularly care about? Like, where exactly does your personal bias for your prior lie? Like, what do I want? What am I after? And so this is where we do this in a confusion matrix. I should have blown this up a little more, but this is what it's called. Is you've got the negative. So the negatives are up here. So the true value is negative, positive, and the predicted label, or the thing that I actually stuck on it, negative and positive, right? So if it's really a negative, and my labeler actually labels it as negative, that is, you know, over here. That's the number of ones that I correctly call as negative. And over here is the ones that I correctly call as positive and that are in fact positive. And then there are ones that are positive but I incorrectly labeled as negative. And here's the ones that are negative that I incorrectly labeled as positives, right? So the confusion matrix, like, these are the ones that are correct and these are the ones that we kind of messed up. Should I switch that one on? Would that be easier? So the confusion matrix for basically calling all their planets uninhabitable is 990 negative were correctly classified, and we misclassified 10 that were positive, and we misclassified as negative, and then basically 0, 0. So if we want the accuracy is living here on the diagonal, and so the accuracy of the prediction was the total positives and the total negatives, these two, divided by the total positive, total negative, false positives, and false negatives. I'm going to have, these are going to show up a lot today. So the accuracy is 99%. Great. But that's not a very good metric, right? Because we're after these. If it's a balanced thing where it's like, yeah, it's close to 50-50. So the accuracy, for instance, of an election, just harking back because, might not stay relevant. An election which is closer to 50-50, the accuracy matters. However, it's completely imbalanced and you're trying to find a few rare apples, then precision and recall are the things that we're after. Who here has heard of precision and recall? Okay, good. I'm also new to this. So the percentage of correct positives, so the ones that we're after, over the total number of positive classifications. So suppose I'm selecting interplanetary destinations, right? So I've got 10 habitable planets. And so I've got 10 positive, so in what I just had, I had 0 destinations over the total positives, right, which are also 0. So basically my precision was terrible, okay? But suppose I get like 2 right. So I got 2 true positives and 8 false positives. These were, right, so these are, I basically have 10 destinations, 8 false positives, 2 true positives. And my precision is only for 20%. Basically, if I send out expeditions, 1 in 4 is going to fail because they ended up at somewhere where they shouldn't be. Yeah? Okay, so if I really care about like the purity of the sample, then I care about the precision. But if I want to make sure that I catch them all, can I make a Pokemon reference here? Yeah? Okay, so that's the recall. I didn't actually play Pokemon, but enough people in astronomy do. And so that's the ones where I have true positives, the number of true positives over the number of true positives and false negatives, right? The ones that actually got in there. And so there's basically 2 ways of assessing how good our algorithm is actually separating out the ones that we want. So the lazy classifier, we have a true positive of 0. So basically precision and recall are both 0. And that's terrible, right? So that's not a good classifier. And so instead of precision, we can think of purity and precision as the level of contamination, the visualization of, and the recall is completeness. How complete is my sample? Did I get them all? And then we have F1, the weighted average of precision and recall. So basically we go like how well do you do between those 2? And so I typically spit out all 3 so that I can go see, all right, how well is it doing? So you end up with a matrix of precisions and recalls as you do different versions of your machine learning. So remember that we had hyperparameters? Vaguely, yeah. So every algorithm has knobs and dials, and you'll end up tuning it one way or another. You either end up giving it a bunch of nodes, like 3 nodes versus 2 nodes, or you say, okay, well, I need my decision tree to go 5 deep, or 20 deep, or something like that. That's a hyperparameter, right? That's something that doesn't have anything to do with the data, but has everything to do with how you run the machine learning. And so every time you do that, you measure these precision, the recall, and the F1, and go like, all right, this version of my machine learning versus this version of my machine learning, which one is performing better? Because I had a test sample, right? I had a training sample that had labels. I trained it on one, and I had a test sample. In the test sample, I determined the precision, the recall, and the F1. Staring everybody in the face so that I can kind of get a feeling of energy / understanding. Okay. So another way is the visual mnemonic. Honestly, I do with the next one, but this works as well. We have the true negative and false negative ones, false positive and true positive. This is the accuracy. These are accurately determined compared to everything, right? So it's green over blue in case you are not colorblind, because if you're colorblind, they look very similar. But it's the green amount. That's the denominator and the blue is the denominator. And so in the precision, you care about how many true positives you have and how many false positives over the total positives you got, right? How many of the positives that I get were actually correct? And in the recall is how many did I lose to false negatives, right? So how much of my data am I missing if I get this? So for example, if you've got good precision, so basically you've got most of them are in here. So you're fine with that. So I've got a pretty pure sample, and I know what this percentage is. I can go, well, for example, I found 10 habitable planets, but I know that there should be 12 because I know what my algorithm's recall is. That's something you can live with, right? It's like there's 2 missing, but I know they're out there. But I know what the percentage should be. With this kind of thing, if you're, for instance, care about how good you are, then yeah, you want the precision to be really high because you don't want people to panic if they get the wrong report. Another way to do this, so I showed this in the assignment 20. Assignment 20 is purely on precision and recall. It's just pure. You run these things. There's nothing to plot. There's only questions to answer about precision and recall. So if you want a quick one to finish off today, go do assignment 20 right after this, right? So you have the relative elements, right? These are the ones that are, you've got the true negatives and you've got the false negatives. So these are the ones that you accidentally tossed. And these are the true positives. These are the ones that you really wanted. And these are the ones that snuck into your selection. And these are the true negatives that you got rid of successfully. So think of it as like a selection procedure, right? So you want something, you want one half, and you want the other half not to be in your sample. This is a very common physics problem, right? I want just the mu tauons and nothing else. Give me just that flavor of neutrino, please, and nothing else. And I keep forgetting what the flavors of neutrinos are, but let's say vanilla. So you want vanilla neutrinos, and you want to drop everything that has mint flavored because, you know, ew. And so in order to do that, these are the ones, there's your vanilla flavored neutrinos, and you want to get rid of all the mint flavored ones. These are the mint flavored ones. These are the mint flavored ones that got in there, and they're going to really mess up your sample. And these are the ones that you missed, right? So the ones that you missed, you can go, well, I'm okay with that provided this is clean. This is a nice clean sample. So that's where my recall is, where my precision is really, really high, right? This is almost unity. That's what I wanted. Or you can go, no, I really need to know how many of those there are. And if the recall is really good, basically nothing gets dropped, I can live with a couple of false positives, right? What's your priority here? And that changes from experiment to experiment. That's why there's no, this is your machine learning algorithm that you want. But before you get started, this is why I'm moving this up. Next class, I'm moving this up like as soon as we start introducing machine learning, because that sets us out on which path do we need to go. What is our measure of success here? Yeah? Okay. So this is good for comparing models. So if we have the same data set and we have these different versions of the model, or we have 2 different classifiers and we want to see which one performs better, the accuracy tells us very little. The precision and the recall is how we tell them apart. And so when we're building these models, when we're iterating them out, and we teach them a couple of times, we can see whether or not the different iterations work with like the precision. Did I want the precision or did I want a recall? And I'm realizing I showed a couple of these examples that I was working on, and I didn't do this. I didn't do this from the outset. I should have said, okay, do I care about precision or do I care about recall? Which one of those 2 is important to me? And so that's the first question you need to do. So hey, if you're reading your paper on machine learning, maybe you should go, what did the authors set out to do? And did they actually set this out, or did they just like, oh, I'll just apply machine learning and see what comes out, right? Which is usually how we go, into machine learning. The thing is, what did they need? Did they need a clean sample, or did they need a complete sample? what was critical for their design. And so, for example, the decision tree with choosing one metric over the other changed the optimal splits or given training set, right? So that can change a lot. We saw that the decision tree changed quite a bit if we added features or not, right? It got deeper, it got closer, and so they have, so we can look at the loss function, which is, we can call the, you calculate this as a function of, now I need to go make sure that the receiving operator characteristics. So essentially, I try to show this with a couple of these things with the self-organizing map and the k-means clustering, right? They all had this like something that you compute as you increase the number of iterations. And so you can do the same thing with the true positive rate and the false positive rate, for example, and can see if this actually improves as I tune a hyperparameter or let it learn some more cycles. Because another problem with machine learning is that you can always let it run longer, but at some point it just iterates around its best solution, and you can't tell because it goes, no, I'm still computing, and so figuring out when it's actually done iterating is a way that you do this. And so another thing that may sound a little familiar, because what happens if our entire set is not that big, right? So that's something that I ran into. My entire data set was 150 examples. So that's not really enough to train on. So how do I improve this? Well, more than one test training split, for example. So we use all the training data. So we split it a couple of times. We avoid the risk of oversplitting, so we don't have to worry about whether or not 20/80 or 70/30. We can just wobble around that forever. And so we can do a non-typical. We can do 50/50, no problem. And then we just do this over and over. And so we don't have to, instead of having one learning set that we're splitting into a test and a training set, we basically do it a couple of times. Why does that sound familiar? What does that remind people of? I'll split my sample and redo it. I'll split my sample and redo it, and then take the average and the standard deviation of the results that I'm getting. This is bootstrapping. It's bootstrapping with machine learning because we have a giant computer that can do it anyway. But it's the same trick. I keep running into this with like, oh wow, this is a cool name, and I'm like, wait, it's almost the same trick. Oh, it is the same, right? There are so many tricks. So this is really what we're doing here is bootstrapping. We're splitting our sample a couple of times, running our machine learning algorithm, and see how well we do, and take the average. So we use all the learning data set. The standard deviation of the scores vector, basically the results, give us an idea of average performance and uncertainty. So we didn't accidentally luck out with our training set and then with our test set and go like, wow, we got a recall of like 80%, we're doing great. And then look, well, if I split it differently, I get a completely different value, right? So that is an outlier effect. You can average over that by simply splitting it and doing it multiple times. This is not a problem if you're dealing with something like k-means or k-nearest neighbor or support vector machines, like all this stuff that a computer does like this. As soon as it's like, well, I have a convolutional network over a million images, this becomes a problem. But fortunately, it's not a million images. You don't have to worry about this as much, right? This is for small samples, but easily computed. Okay? So the bad thing was, take 5 times more to run. But if that's not a big deal, because it's easy anyway, and all the algorithms we use so far, the sklearn algorithms are all super quick because they're supposed to teach you. Okay. So if we're diagnosing a machine learning algorithm, you can either have bias, as in my input sample had a bias in it, or you can I've now tailored it so much to my training set that it actually does not predict at all. So, and you're sort of oscillating between those two options. You either bias yourself or you have variance. So you underfit or you overfit. Hey, that sounds familiar. Right? There's nothing really new about machine learning. They do the same things, right? We can do the same tricks, and we can use the terms underfitting and overfitting. So either I don't have the complexity of the whole thing, so for instance, I just do one cut. I have a decision tree of one, and it's like good, bad, and then I am biasing myself. Or I can split to the point that I have now split so far that it only works for the training set and not on the test sets anymore. So there's basically I can underdo it or I can overdo it. And that's where sort of you come in as you have to evaluate how well it's actually doing. So a good example, like that's exactly what this is, right? We're leaving it completely empty, like how it's fitting it just right, and we have the too high variance, which has so many over-parameters into it that really the minute I get a new data point, it's completely off base. Same thing. Minimizing your line or your model to it, it's the exact same effect. That hasn't gone magically away, despite the fact that we threw this magical black box called machine learning at it. And so same thing goes here. Like you have your training set, you selected a couple of red points as your validation set, as your test set, and you have your line here, and you go like, well, this is how well I do with the hyperparameters where it has to be a line, right? So that's the model that you kind of gave it. But it only has two free variables, an intercept and a slope, and so it did its best. And then even then, if you look at it with the test set, it does okay, and you're like, all right, well, this is how well it does. But suppose I gave it infinite number of free parameters, it just fits this insane function to it. But the minute I give it a test set, you realize that it's way off base. Yeah, same thing happens with the chi-squares, really, because it should. They should give the same results for a simple model, right? So this is a high bias. We actually gave it the train and test errors are similar. So the chi-squares are 0.7. So they're really like it's not. There's a lot of space between your model and the data, but they're similar, but they're high. So it's a high variance, but they're similar. As soon as there's a big my train error is like next to 0, is very good, and then as soon as I test it, it's like there's a huge gap. That's when I overfit, right? So if training and test results are far apart, that's overfitting. If they're similar but very high, then I'm still biased. Then I can still introduce more complexity. So improving from high bias, try different features, try engineering new features, try like more complexity. You can add complexity. There's still room. That's how you should see it. Test and training agree, like their chi-squares agree. Their recall and their precision agree, but they're not great. But so you can say like, well, I can add more features. I can add more information. I can add more complexity. If I have way too high variance, my training set does perfectly and my test set bombs, right? That's where that's the worst thing to run into is like what do I do now? Do I remove features? Because sometimes you realize like, yeah, the thing actually did nothing. It just added noise. And try less complex. So basically bias, add complexity, or there's room to add complexity. You don't have to, but you can. And then there's although if you want to get a good result, you probably want to add some complexity. And if there's high variance, you basically overshot your target, and now you need to simplify things. That's harder, to be honest. I find simplifying things incredibly hard. Anyway, so check, do I need more training data? Because basically this can happen when I have not a big training set. This can happen when I have not a big training set. So it's like maybe just throwing more data at the problem, although that's a knee-jerk reaction from an astronomer, right? So it's always throw more data at the problem, then it might go away. This is not mutually exclusive, so it is more of a diagnostic tool. So learning curves, if you have this variance and you see your training score and your test score, And if they're still improving as I'm, for instance, increasing my training set, if I'm increasing my data set, that's when it's like, oh, I can do better. Or, for example, I can still keep training, for example. Like this can also be number of cycles that I threw at it. And if as soon as it flattens out, you go like, all right, well, that's as good as we can do. It's no longer improving. Extra data doesn't help, or extra cycles won't help. So that's where these learning curves come from. So this is the thing that machine learning people stare at. They were waiting for that learning curve to basically start flattening out, and they go like, okay, great. This is where I can cut my algorithm. So if the scores are still changing, keep, patience, and then curve is flat, great. Call it a day. So which algorithm is best? And best is something, again, that you need to sort of define before you get started, so you know what you're working towards. This is true for everything in science, by the way. It's like as soon as you have a fixed goal, I want to answer this. This is my thing. I want to see what the percentage of this is. Or is this true? Yes, no. I love yes, no questions in science because at least there's the least amount of ambiguity. It's either yes, no, usually end up with a maybe, but still, it's like 3. And so which algorithm is best? The high bias, low variance, high variance, low bias, or the lowest gap between training and test set, and the highest test score. So there's a bit like, what are you after? So do you want your train and test set to mimic each other the most? That's great, right? Even if your precision or your recall aren't great, so suppose it's 80%, you miss 20% of the ones that you're going for, but at least you know that. You can keep that into account, for example. So you want this would be fantastic for certain kind of applications, right? If I want to know not exactly which ones there are, but how many stars are of this particular variant, right? How many G-type stars do we have in the Milky Way? And I go through all of them that I have data for. If I go, well, my training set says this much, and I'm 80% precise, I can compensate for the remainder because I just wanted the number. I didn't want to know exactly where all of them were. But if I go, no, I need to know exactly where all of them are because I'm going to point precious telescope time at them, then, for example, I want really high precision. And so maybe my low bias and a high variance, that's fine. Right? So this is the kind of thing, like, it depends on the kind of problem that you're dealing with. Okay? Yeah. And so highest test scores, that's why you build these confusion matrices based on your test data. So like, how well are we doing? For instance, if you have multiple classes, this is no longer positive, negative, but for example, you have 3 classes, then you end up with class 1, 2, 3, and the numbers that are off. So you want everything as much populated along the diagonal. So how to this is Vivian's summary. So you choose the model, but basically first, what is the metric you're after? That's my step 0. What is your end goal? Because you can then scratch that out here and then figure out, then you can loop through these, which is essentially saying, all right, this is what I want to do. I want to select all the habitable ones. If that's my goal, or I want to accurately predict. So in that case, I also want to know what non-habitable means, right? So those are then equally balanced, just an unbalanced data set, but equally important classifications. Or cats and dogs, right? So I want to have all the cat pictures in the world, but I don't care if it's a dog, right? So then one of them is positive, one of them is negative. I don't care. It's like it's basically cat, non-cat picture classification. And so choose the hyperparameters by, so this is alternatively optimize hyperparameters later. I'll be honest, I'm usually of this category. I'll run it out of the box and see what happens, and then go back and go like twiddle with the hyperparameters. So we know what the features are. This is the cleaning part, and then split it into test training set. That's what we've been doing. Fit the model to your data with the fit, and then model new, and then as you go through, you basically loop through these middle ones as you improve your recall and precision. Okay, You always have to have a Gilbert or something in there. So that was the part that I wanted to talk about. I will, having now learned from how we introduce these various topics, I will move this next year earlier because I feel like this was a useful thing to know as we got started on things like self-organizing maps and k-means clustering, etc. Now I want to talk about this. I don't know about you, but this third pandemic semester is doing a number on me, so I would really appreciate it if we can figure out where we want to go from here. Most of you have gotten about a dozen of the Jupyter notebooks in. Is it like how are we doing with the final paper? Is everybody feeling okay about that? Okay, there's at least one shaking head already. And so I want to make sure that we can reasonably get to the end. That is my entire goal. I couldn't find a picture of that plane engine on fire, but I keep thinking of it. So Jupyter Notebook assignments, most of you have to have about a dozen. I'm willing to just call that okay and call that, it's like a dozen is fine. If you want to do more, great, I will grade them, but a dozen is fine as far as I'm concerned. You're safe. And then how can we help each other over the finish line? Are there other people that are like in the class? I know a few more are struggling, so reach out to them and see if you can help them with what you've got. What can I do to help is where I'm at now. So we've got a little bit left in the semester, and I just want to bring this into it for a landing. I say fully aware that I'm being recorded, so it's a bit awkward. So yes. Not do the paper. No, I mean, stuff is on the table, right? So if you are struggling with the paper and you go like, I need more time, or I would like to do, can I just do Jupyter Notebooks, and can I be graded on that? I'm okay with, you know, if you're going to like, I would like a solution like that. Okay, I'm open for these things, right? This is not a normal semester. This has nowhere near been a normal semester for me. So I'm putting this up here because hopefully this helps a little bit if you do want to do the final paper. You go like, no, I like the final paper part. Or for example, I don't have a lot of Jupyter notebooks, so I would like the final paper to count a little heavier. I'm okay adjusting as needed, basically playing towards. I understand that other people who have already heavily put in the Jupyter notebooks are now going like, well, I did them all in. It's like, good for you, great. We all had a various level of not great semester, I think. So I think I'm adjusting for each of you personally. I prefer to do that. So if you want to do the final paper, you go like, I would prefer the final paper to be my final grade, or the final paper to count more heavily, then I'm also happy to do that. But let me know, because then I can say this is what I'll use for your pass fail or final grade. I just wanted to put this up here because basically these are the questions I want you to answer. It doesn't have to be a huge thing. Basically, copy and paste these questions and answer them about this paper. These are your writing prompts, and they don't have to be paragraph-long answers. I'm perfectly fine. Like, is it ethical to use this way? No. I'd prefer if you say why, but still, you can. That's a full answer. And so these are your writing prompts for the final paper. That should hopefully make it a little easier. I always find like a completely blank, write your answers here page horrible. So these are your writing prompts. Like answer these things, 1, 2, 3, 4, 5, 6, 7, 6 plus a bonus. And then I have these are the questions. This is what I have next to your paper as I evaluate it. So I realize we all have a different approach to these things. So some people prefer to do the Jupyter notebooks, do assignments. I purposely did not give deadlines because weeks tended to explode for different people at different times. But I also wanted to make sure that if you go like, well, I now want to do I'm not a big fan of the final magic last 3 seconds, shot to finish the game. Mostly because I usually miss the 3-pointer. But you can pick this as your, like, well, can you grade on this mostly, or can you grade mostly on the Jupyter notebooks? I prefer one or the other. Let me know, because I want to work with everybody here to get to the end. That was a long-winded way of like, hey, do you want this? I want the numbers to change a little bit in the final evaluation. I'm happy if you've done about a dozen Jupyter notebooks, then I'm already good to check you off. Okay? I prefer this, by the way.
That people have individual differences, or are you asking us as a group right now?
As a group.
Okay, so are you proposing that if we choose, we can say we would rather add 5 or so more assignments to your, 12 that you said is good, in lieu of the paper?
If that's something that you'd rather go for, let me know. If you'd rather go like, well, I now know what to do for the final paper. I'm basically putting everything on the tables just to make sure that there's 2 different groups here. There's grad students and there are undergrads. Undergrads need a grade, and they can say, I would like my grade to be based on my paper more than on the Jupyter notebooks, or you can say, I would keep it as is. For the grad students, I mean, I'm really open to modify. This was what I came up with at the beginning of the semester, knowing already that it was a weird semester and nothing was normal. So happy to work with you to figure out what the best solution is. There's nothing set in stone that it has to be X number of Jupyter notebooks. I just offer them, seeing which ones worked well with you. So if you have suggestions, I am open to those. You can email. Yes.
I like the suggestion Taylor said about maybe an X number of Jupyter notebooks plus 12 for presentation.
If you prefer, like, you go like, yeah, I've written enough papers for English classes already, I'm good with that, then you can say, yeah, then I'll base it on the Jupyter notebooks, and you can just put as many of those in as you want. If you are more of the, so what do you, okay, here it is. Do you want a single, do you think that is the best way to do it? So people can either pick for a final paper, or they can give me extra Jupyter notebooks. Is that fair?
Because it doesn't hurt the people that have already done a significant amount of Jupyter notebooks.
Yeah.
It helps the people that maybe have not or want to do one thing or the other.
Okay. See, I want to get an equitable solution, and I know that I have a room full of smart people, so I can probably get there with you all, right? So let's say you need to have 12 in, and a final paper, or you do as many Jupyter notebooks as practical, and I base it off that. Does that work for everybody? Yes.
Does this mean notes are no longer going to be effective?
That was a tryout. So a lot of this class was me trying stuff out for the first time. You are the guinea pigs. Yes. Welcome, first pancakes. What I noticed in my last 100 class was that they did really well because they were all completely spaced apart, and I needed some way for them to collaborate. And I just offhandedly mentioned that they could take notes together, and they did really well as a result, because it's kind of like you collaborate but at a distance. And so that's what I was hoping to foster with this, but I'm realizing that maybe LaTeX is not the easiest place to do this, so I'm totally doing a Google Doc next time. But that was the goal. If you have literally opened it once, you already got the 10 points. I'm fine with that. I was just very curious if this would work at a grad school level as well. See where the idea came from? Because again, I'm not sure if you're all getting together later after all this, or if everybody's working in their own isolation pod. I have been working in my own isolation pod. My kids are going up the wall, so. They are back in school, and it's been interesting. It's very quiet for a whole Monday and Tuesday. Yeah, it's like crashing into something else by now. So if this is a preferred way, because I want to make sure that we can get there one way or another, right? I'm totally borrowing from my kids' school. It's like, yeah, if you can do this, great. If you can do that, great. It's all going towards your final grade. So if you prefer, hey, I like doing, and I think I got everything from the Jupyter notebooks that I need to get, do that. If you kind of go, I've got already a dozen in, and I'm actually blowing through them at a ridiculous speed, great, do that. I will base it on that. But let me know beforehand so that I have something to cover my hiney with, that I say, like, yeah, that we agreed on doing this as a group. I'm totally stealing this from Viviane, by the way. She was always like, yeah, well, she dropped the final. Because this Viviane Acquaviva, and she was like, yeah, I dropped the final because it was just not working. So if these things work for you guys and it frees up some of the pressure from the full semester, great, that's what I'm here for. But if you want to do the paper, great. If you want to do the Jupyter notebooks, also fine. Let me know.
So I just want to be clear, you're offering 2 options.
Classes. Undergrads, also let me know, because then I can just basically base it accordingly. Anything that helps you get through the last few weeks. English through the last few weeks, right? This is a weird semester. Let's not pretend otherwise. Next week, I got my second shot. Get yours. Anything else I can help people with? No? How are we doing for time? Way too fast. That's fine. No, I just wanted to make group. Thank you for all being here, because it's a lot easier for me to figure that out than trying to do this over text and what have you. But if this works and you think this will work for most people, then and contact your peers and see if anybody else needs some help with the last Jupyter notebooks. Maybe you can help them over Zoom or something. But if you think that you think this will work, okay, good. Yay. Well, that's the rattle to the end of the semester. I'm going to go stop recording now.